Hello friends, my name is Qian. Today I will talk about limitations of single-step drift minorization in convergence analysis of Markov chains. Drift minorization is a commonly used tool for convergence analysis, in particular for constructing convergence bonds for Markov chains. It has been observed that the convergence rate bonds constructed by this type of arguments are usually overly conservative, especially in high-dimensional situations. However, there hasn't been a lot of studies on, well, a lot of rigorous studies on this phenomenon. So in this work, I will present a framework that allows one to quantify this limitation of drift and minorization. Consider a Markov chain axiom that converges in distribution to pi. This is a common scenario in MCMC where we use a finite portion of the chain as an approximate sample from pi, the stationary distribution. In order for MCMC to work well, we need the chain to converge relatively rapidly to the stationary distribution. And thus it is important for us to quantify the rate at which the chain axiom converges to pi. We often want the chain to be geometrically ergodic in the sense that the total variation distance, d sub tv, between the distribution of the nth element of the chain and the stationary distribution pi decreases at a geometric rate or exponential rate with regard to the number of steps m, meaning that this distance is upper bounded by a certain function c of x, where x is the initial state, multiplied by rho to the nth power, where rho is smaller than 1. For a given Markov chain, if I allow this c of x to vary, this function c to vary, then it could satisfy this inequality with multiple values of rho. But there's an infimum of them, and this will be the true convergence rate of the chain, which we denote by rho star. Rho star is a number between 0 and 1. A smaller true convergence rate rho star indicates faster convergence in the long run, and a rho star that's close to 1 indicates slow convergence, at least in the long run. So convergence analysis is basically, it focuses on bounding the total variation distance between the chain and the stationary distribution, or bounding the convergence rate rho star based on the transition law of the chain. For a time homogeneous Markov chain, its transition law can be characterized by its single-step transition kernel, which I denote by capital P. And capital P basically tells you what the distribution of the next state xm plus 1 is, given that the current state xm is at a certain point. So for a Markov chain with transition kernel P, I would denote its convergence rate by rho star or P. A very commonly used tool for constructing upper bounds on the true convergence rate rho star of P based on the mathematical form of P is called the drift minorization argument. It has two basic elements: a small set C, which is a subset of the state space, and the drift function V, which is a positive function over the state space. Both these two elements, the C and V, are actually manually constructed. In other words, if a researcher is presented with a transition kernel P and they want to bound the true convergence rate rho star of P, what they first do is that they construct or find a reasonable choice of C and V, and then they establish a set of drift and minorization conditions that basically says that the chain forgets about some of its past whenever it enters C, and if it is outside C, it drifts back towards C after one iteration. And the intuition behind this type of argument is basically that if you want the Markov chain to converge to its stationary distribution, it needs to converge regardless of where it comes from. So the ability to converge coincides with the ability to forget about its past. So there are multiple versions of drift minorization in the literature, but they more or less look alike each other. And here's a very typical set of drift fund minorization conditions, which I call A1 and A2. A2 here is the minorization condition, and A1 here is the drift condition. And as you can see here, in order to establish these conditions, you first need a choice of drift function V and small set c. The minorization condition basically says that whenever the chain is currently in the small set c, after one iteration, it forgets some of its past. And the drift condition basically says that whenever the Markov chain is currently outside C, it tends to drift back towards C, so that in the long run, it visits the small set C frequently. The strength of these two conditions are quantified by three parameters, lambda, k, and epsilon. Essentially, epsilon quantifies how much the chain forgets about its past after one iteration if it has entered the small set C. And lambda and k quantifies how frequently the Markov chain will visit the small set C. Based on the values of lambda, k, and epsilon, one can construct a quantitative upper bound on the true convergence rate rho star, which is a function of lambda, k, and epsilon. And there are a lot of important results in this direction. This is important in theory and practice because if you recall, rho star of P is a true convergence rate, and rho star being large means that the chain converges slowly, rho star being small means that the chain converges rapidly. So an upper bound on rho star tells you at least how fast the Markov chain converges. As I said, there are lots of results in this direction. There are lots of different versions of convergence rate bounds based on a set of drift fund minorization conditions. Again, they look pretty similar to each other, although some are better than the others, probably. And here's a very typical result, a pretty standard one, by Baxendale, which says that if I have a transition kernel P that satisfies these two conditions with parameter values lambda, k, and epsilon, and that P also satisfies a few other regularity conditions, then the true convergence rate rho star of P is upper bounded by this function of lambda, k, and epsilon. Alpha here is a function of lambda, k, and epsilon. Okay, so a user of this theorem will be presented with the P, and then they construct a V and C and establish A1, A2 with a certain numerical value of lambda, k, and epsilon, and they plug these values into this formula, and they get an upper bound. This type of results has been very, very useful, especially when one wants to establish the so-called geometrical validity, that is to prove that rho star of P is strictly less than 1. However, people have observed that as a quantitative bound, this bound here, and among others, tends to be overly conservative, especially in high-dimensional settings. There are cases where we know that the chain converges rapidly, that is, the rho star is small. However, the bound that we construct based on this type of theorems is very close to 1 and very far away from the truth. Here's a very simple example. Consider an n-dimensional Gaussian autoregressive chain that is, so given the current state xm, the next state xm plus 1 follows an n-dimensional Gaussian distribution with mean xm over 2 and a constant variance. Of course, this chain is very simple. We know everything about it. We know that the stationary distribution it converges to is an n-dimensional standard Gaussian, and its true convergence rate rho star is actually exactly 0.5. So the chain actually converges pretty rapidly, and this true convergence rate is independent of the dimension of the state space, and it's always 0.5. However, if we pretend that we don't know this and try to apply drift fund minorization to this problem, say let's try to apply Baxendale's bound to this Markov chain. Let's pick n to be 10, so it's a 10-dimensional Markov chain. The first thing we need to do is, of course, to pick a drift function V and a small set C. This is here's a very standard construction where we choose a drift function to be a quadratic function and a small set C to be a level set of the drift function V. And then we try to establish A1, A2. We need to do a little bit of work, but in the end, you can establish A1, A2 with this choice of V and C with this parameter value lambda, k, and epsilon be equal to these, right? And then you plug these numbers into Baxendale's bond, and the upper bound that you get is 0.9994. So if you plug lambda k and epsilon into this formula, you get 0.99994, which is very close to the maximal value 1, but very far away from the truth, 0.5. So you can see this bond is very, very conservative. And it gets worse if n is larger. And this, as I said, this is a common phenomenon, especially in high dimensional settings. And this makes people worried. Is it true that drift on minorization is actually incapable of producing sharp upper bonds on the true convergence rate rho star P? Or maybe it's just that when we are using this argument, we are not doing good enough. Perhaps the bond that we're using is far from optimal. Perhaps this bond constructed by Baxendale isn't all that good. Maybe this inequality still holds if I square this upper bond. Who knows? Or perhaps that this bond is actually pretty good. However, our choice of the drift function v and a small set c are not very good, resulting in poor values of lambda k and epsilon. Perhaps if I chose a different drift function v and a different small set c, I get much better values of lambda k and epsilon. After I plug them into Baxendale's bond right here, I get a number that's actually very close to 0.5. That could be true as well. Okay? So obviously, this is kind of a hard problem to judge, because there are basically infinitely many choices of drift function v and small set c for a given Markov chain. So in this work, we built a framework that allows one to eliminate these two possibilities for a given Markov chain and conclude that for that particular transition kernel, it is impossible to construct sharp bonds based on single-step drift harmonization, A1 and A2. By the way, I forgot to mention that A1 and A2 are called single-step drift harmonization because they only concern the one-step transition kernel P. Right? There are versions of drift harmonization that concern the multi-step transition kernel P, which captures basically the distribution of the Markov chain after multiple steps or multiple iterations. And those bonds tend to work pretty well in high-dimensional settings. The problem is that for MCMC algorithms, the transition kernels are usually pretty complicated, and getting a handle on the single-step transition kernel is hard enough. Basically, you have no hope of doing any concrete analysis if you start from a multi-step transition kernel. Right? So this is why we focus on single-step drift harmonization in this talk. All right. So okay. So let me now introduce, give a very loose description of our framework. Let's try to deal with the second possibility first. That is, maybe for a given value of lambda k and epsilon, this bond isn't optimal. Okay. So what we're going to do is that suppose that I have a generic Markov chain that satisfies A1, A2 with a certain values of lambda k and epsilon. Then what is the optimal bond on this true convergence rate based on these parameters? A convergence rate bond should be a function of lambda k and epsilon, like the one given by Baxendale. This alpha, if you recall, depends on lambda k and epsilon. Moreover, this bond should be universal in the sense that it should dominate the true convergence rate of any transition kernel P prime that satisfy A1, A2 with these parameter values, not just the convergence rate of the chain that we're studying. And thus, the optimal convergence rate bond, well, it should be smaller than any existing bond, like this one that we introduced previously, but it should be lower bounded by the convergence rate of any transition kernel that satisfy A1, A2 with these parameter values. Essentially, we can say that the optimal convergence rate bond based on this value of lambda k and epsilon is the convergence rate rho star of the Markov chain, of the slowest Markov chain that satisfy A1, A2 with these values of lambda k and epsilon. And thus, if we want to construct a sharp lower bound on this optimal convergence bond, all we need to do is find a Markov chain that satisfies A1 and A2 with these parameter values, and that is converges sufficiently slowly. Right? And that is exactly what we did. I'm not going to talk about the exact construction. It's actually pretty simple. But in the end, you can actually find a lower bound on the optimal convergence rate as follows. Right? And if you compare this with Baxendale's upper bound, you can actually see that they are pretty similar. They almost coincide. The only difference is that in Baxendale's bound, you have alpha here. In this lower bound here, you have the largest integer that does not exceed alpha. Alpha is usually moderately large, and so basically this upper and lower bound coincide. And this really tells us that the upper bound constructed by Baxendale is pretty close to optimal. You cannot do much better than this, right? So this eliminates the second possibility. Well, there's still the third possibility. For a given Markov chain, maybe if I pick a different drift function v or small set c, I get better bonds. I get better values of lambda, k, and epsilon, and thus I get better upper bonds. And this is certainly possible. So if I am given a transition kernel P, then the chain-specific optimal bond, the optimal bond for the true convergence rate rho star of P, that can be constructed on A1 and A2 should be the infimum of the parameter-specific optimal bond that we just described previously, where the infimum is taken over all possible values of lambda, k, and epsilon. That is, all values of lambda, k, and epsilon, which P satisfy A1 and A2 with. Okay, and that is allowing the variations in the drift function V and the small set C. You can be very creative with your choice of drift function V and small set C. Maybe you will yield better values of lambda, k, and epsilon. Okay, so the chain-specific optimal bond to study to get a handle on it, we actually need to take into account all possible choices of V and C. And this is obviously pretty difficult, but we developed some techniques that allows one to basically restrict their attention to a smaller space to searching and to basically get a further lower bound on this infimum. All right. I'm not going to talk about the actual construction because it's pretty technical, but what is important that basically we in the end, we are able to build a framework that allows one to get a lower bound on the chain-specific optimal bound for any given transition kernel P. Well, at least for ones that are simple enough to analyze using our method. Okay. So we applied this to a few examples. As illustration, let's look at the Gaussian autoregressive chain that we talked about previously, right? So recall that the true convergence rate when the dimension is 10 is 0.5. In fact, it's actually independent of dimension. And the the convergence rate bound, the upper bound on the true convergence rate we constructed based on Baxendale's result was very conservative, 0.9994. Using the method I described previously, you can actually prove that the optimal bond you can construct based on A1 and A2, allowing your choice of drift function V and small set C to vary, it's lower bounded by 0.922. So this is a lot smaller than the bound we actually constructed. So maybe if we were smarter with our choice of drift function and small set, we could do better. However, it is still very conservative, a lot larger than true convergence rate, 0.5. So no matter how hard you work to find a great drift function V and a small set C, and no matter how hard you work to find a great generic upper bound on rho star, okay, but even better than the one Baxendale constructed, you are still very, the bound that you construct is still going to be very far away from sharp, right? So at least for this example, we can eliminate the second and third possibility and conclude that it is impossible to construct a sharp bound on rho star based only on A1 and A2. This is just an application of our general framework. In our paper, we apply this to a few other examples, and a similar phenomena occurs in high-dimensional settings. So as a summary, we build a framework allowing one to get a handle on the optimal convergence rate bound based on a set of single-step tree-form minorization conditions, and thus quantifying the limitations of this argument. This does not mean that tree-form minorization is incapable of finding sharp convergence rate bounds. There are indeed cases where it works pretty good, but this is this is a kind of negative result that signals cautions, or well, people already know that this method tends to work poorly in high-dimensional settings. But this here we build a framework that kind of rigorously allows one to prove that it doesn't work in certain settings. Right? As I said, if one has a handle on the multi-step transition kernel, they can try to establish multi-step tree-form minorization, and this can circumvent the problem. This is usually very difficult in practice because, as I said, multi-step transition kernels are usually intractable, but one can try to construct smart coupling schemes or use different types of distances between distributions to capture the long-term dynamic of the Markov chain. And this sometimes yields pretty well-behaved bounds in high-dimensional settings as well. All right, so this is the end of my talk. Thank you for your attention. If you are interested in the references I mentioned in this talk, they're given here. The main results of this talk are given in this paper. Again, thank you.